Hey there, welcome back. So in this video, we're going to take a little closer look at what's happening behind the scenes in precipitation reactions or double displacement reactions. So we're going to be taking a look at a couple of examples where we take two clear solutions, combine them together, and produce a solid, kind of like the pictures that are on the screen there. When I say a precipitation or a precipitate, this is what precipitates look like. You've got two clear solutions, and yet there's this cloudy, oftentimes white, but could be an interesting color solid that forms from this. So we're going to be looking at this more in a paper ratio, written balance equations, that kind of stuff, rather than actual, chemical reactions. But you'll get an idea of kind of how to predict the products and what's happening in a double displacement reaction. So definitely more of a practice kind of a video here. So just as a reminder, precipitation reactions, when we use that particular phrase, we're not talking about making it rain. We're talking about double displacement reactions, ion exchange. And we're taking two aqueous solutions, combining them together, and hopefully or potentially producing a solid product as well as another product. So why is that? What's happening kind of, like I said, behind the scenes? So remember, the most important thing to kind of start off with is what actually happens when we make those original solutions. Those original solutions, no matter how we write them, contain ions. So remember, when you have a solid, a salt of some sort, this one shows sodium and chloride, and we put it in water, that original particle starts to break apart into smaller things, and eventually you will get a situation like in C here, where they are dissociated ions, where you literally have little sodium ions and then you have little chloride ions, and they're sort of swimming about, so to speak. But again, this is dissociation. A lot of times when we're handed a clear solution, we forget that this process had to have occurred. So you see a solution that's just labeled NaCl, and it's kind of logical to think that there's sodium chlorides in there, but there isn't. What's actually in there is a mixture of sodium ions, chloride ions, and water molecules. When we do this sort of a process with compounds that contain polyatomic ions, something similar happens, but when we did the sodium chloride, it was pretty easy because you just had Na and Cl, and when this thing broke apart, you had sodium ions and chloride ions. But what about something with a polyatomic? So like this one on the screen right here is silver nitrate, AgNO3. When we take solid silver nitrate, and it looks just like salt, it looks like a white crystalline solid, and we dissolve that in water, it splits apart, but not 100%. And this is important to remember, that it splits apart into its component ions, which are silver ions and nitrate ions. The nitrate ions, you can kind of see them in here, stay as a little cluster. They function as a team. That's what makes them a polyatomic ion. They're not individual ions. It doesn't separate out into nitrogens and oxygens. It stays as a polyatomic group. So that's a really important thing to kind of keep in mind. And so when we splash these things together, they're kind of separated and sort of, like I said, swimming around, sort of a pool party. So what does this look like when we start combining two solutions? So this is a very cheesy model of a double displacement reaction. So here we're starting off with a compound, an ionic compound. That's the compound AB. And we can say that these guys are the A ones and these guys are the B ones if you wish. Doesn't really matter. I think A is yellow and B is blue. And then we have a second compound, C and D. C is the green ones and D is the purple ones. So when we take two solutions and combine them together, what's actually happening? Well, first of all, when you combine that solution together, you've got to recognize or realize that the first thing that happens is dissociation. So what we've got here is you'll end up with a mixture. I don't need the C and the D, sorry. You'll end up with a mixture of these guys all sort of spreading throughout the solution, through the water, whatever it is, and they'll sort of kind of mix up. Okay, fine. So now we've got a solution of C ions and D ions, and they're going to be moving and bouncing around all over the place. If we also then add in this compound AB, we're going to have a similar mixture. Again, pool party. We're going to have these guys are going to start separating out, and they're going to sort of all intermix. Well, so what? I don't need the AB. There you go. So what actually happens here? Well, remember what we had to begin with. There we go. I'll get these guys all dissolved. Yay, there's a pool party. Lots of ions all hanging out doing their thing, right? So we're now at this particular phase right here where we've got just our reactants together. So we've kind of simulated sort of this spot where we've got A and B, C and D are sort of combined. They have dissociated, but they haven't potentially reacted yet. Well, so now what? Well, these ions are going to start sort of bouncing around. They're not going to stay in one spot. These things are moving all the time as they shift around and sort of move through this particular solution. And if you mix it, all kinds of things happen. And they keep kind of moving and sort of bouncing into one another and meeting each other, so to speak. What there is that happens is the potential for new ion combinations. So remember what our original ion combinations was. So this was our original combination of A and B together. We know that when we put this in water, it's soluble, that the ions are going to separate, that the attraction between the ions in the water is greater than the attraction of the ions to each other. That's what soluble means. And the same thing was true with C and D. When those guys were together, we put them in water and they separated. They dissociated out into their separate ions. They prefer to be with water than they prefer to be with each other. They like each other just fine, but they're not stuck together. So they separated out. So now what's going to happen when these guys come into contact with one another? Well, in solution, these things are going to literally be sort of floating around. They bounce off of stuff and kind of meet each other. And these two could potentially meet. Well, this is B and D. And notice I've kind of got the outside boundaries here so we can kind of see what the matches are. These two are both negative ions. These guys are. So what happens when these two come into contact? Well, actually, legit nothing happens because they're both negative. They're going to kind of come close to each other, but then they would kind of repel and sort of move away from one another. So they would never quite come into contact. The same thing is true if we get two of our positive ions together, right? If we've got A and C, when these guys are bouncing around and kind of meeting up and bouncing around, when these see each other, they're sort of going to kind of deflect off of each other, right? They kind of do that sort of thing, right? Because they're both positive and like charges repel one another. So what happens when A and B meet each other? Well, when A and B one another, A and B beat, nice. When A and B meet one another, they are attracted to one another, but then they're also still surrounded by water. So even though they will come into contact, they will eventually split back apart again. They're soluble. Same thing is going to happen when C and D, right? These guys are going to bounce around, they'll meet each other. Hey, how's it going? Nice to see you. But again, we know that these two are soluble. So even if they come together, they'll be together for a second and then they'll bounce apart. But it could happen that new ion combinations occur. Now, this ion combination that we have here did not exist in the original solutions. Remember, it was A and B together and C and D together. So it was yellow and blue and green and purple. Now we have some new combinations. So what could happen here? Well, one of two things can happen. When you have new ion combinations, two things could potentially occur. Option number one is they come together and it's like, oh yeah, you're cool, but not that cool, right? They meet, but yet they're not that strongly attracted to one another. They simply meet and then they redissolve, redissociate. Okay, fine. That's no reaction. But it could happen that when these two meet, that they become so strongly attracted to one another that they stay together. And at every time they come into contact, as all these guys are sort of bouncing around and doing their thing, okay, nothing. Ooh, hello. Fabulous, right? These guys are bouncing around, bouncing, doing their thing. Nothing's happening. Okay, fine. These guys are bouncing around. Oh, wait, when those two meet, they start to meet. And as these ions start to sort of randomly collide with one another and come into contact, if conditions are just right, the intramolecular attraction is so strong that they stay stuck together. And as they do this, they become heavier, right? Two atoms is heavier than one. And so what we can actually get is this little combination, this pair of ions can actually then settle down to the bottom. And when they do this enough, I'll kind of just do them like this. They settle down like that, right? This guy's still floating around. These guys can start to kind of settle down. These guys would start to settle down because they're just a little bit heavier. All of this stuff is going to keep sort of bouncing around and seeing what happens. Nothing. But again, as these start to, oh, hello, they meet one another, they would start to settle out. And eventually, these guys are already together, they would settle out. So after time, what do you get? Well, after time, you get a precipitate. The intramolecular attraction is too strong. They will settle to the bottom as a cloudy solid and usually settle to the bottom as a layer. And then you'll have all these other leftover ions kind of hanging around up at the top, still just sort of floating around. That's it. That's what a double displacement reaction is. So what we're doing when we are drawing these, when we're trying to predict what our product is, what we are literally looking at is, okay, what was our original pairs of ions? what are the new possible combinations that could form? Our new possible combinations A and B and C and D, right? We could have A and B could meet one another. Well, we know that those are soluble. We could have A and C meet one another, but they're both positive, so they will repel. We could have B and D meet one another, is a possibility, but B and D are both negative, they'll repel. Or your final choice is you could have C and D come together. That's a possible new combination, and that's a possible new combination. One or the other of them may form a product. And that's what we are kind of representing when we draw it like this. We're not really saying which one could be the combination. We're just saying, hey, this is a new possible product, and this is a new possible product. So again, I kind of think of it as like foil, inside, outside, something along those lines when we draw those guys together. Your new possible combination, new possible cation, anion combinations, and maybe, if you're lucky, a precipitate. So in the next video, we'll take a look at how do we record that, how do we write it down, and how do we predict what that product could possibly be. Thanks, I hope you liked it. Just a quick overview, review of precipitation reactions.